We are going to discuss the basic um, modeling concepts using bond graphs. So we have looked in a previous video at what the cause and effect is between two elements, and now it's time to relate those to the different systems that we see in nature. So let's take a look at some of these examples in different energy domains, and you'll see that in here you have a mass that moves. In this other case, we have an electrical system with a voltage input and a resistor, just to make it simple, and current circulates through it. We have a rotational system, which is a wheel in this case, and the variables on this wheel is actually the torque that is applied. As if a torque is applied, then you have an angular velocity that results. You have on this one, here's a hydraulic system where the variables in question are the pressure and the volume flow rate. So you see, the idea behind this slide that I'm showing you here is that systems in nature, they could be in different energy domains, but they share a common set of families of variables. What do I mean with this? In the case of the mechanical system at the top left, you have the force and the velocity. On the electrical system, you have the voltage and the current. On the rotational system, you have the torque and the angular velocity. And on the hydraulic system, you have the pressure and the volume flow rate. So what happens is that if you reflect a little bit on this type of variables, that what we have in here is that you have a force. On this case, you have a voltage. In this case, you have a torque. In this case, you have pressure. This variable, F, and then B, and then T, and then P, this is one family of variables, one type of variables. And the velocity here, or the current here, or the angular velocity here, or the volume flow rate in here, is another family of variables, also of the same kind of variables, but in different energy domains. They have different units, but they are the same kind of variables because the product of those two is always power. Force times velocity is power, voltage times current is power, torque times angular velocity is power, volume flow rate times the pressure is power. To make life simple, we will follow a renaming of these variables with some generalized name. The force, voltage, torque, and pressure in this case, that group of variables are going to be called effort variables. The other ones, the velocity and the current, and the angular velocity and the volume flow rate, they are the flow variables. So we have these two variables are going to be the ones that interact with the other elements in the system, and the ones that we want to use to find out the constitutive laws of each element. So let's take a look in here at the making a summary of what I said. You see on the left hand side we have the effort variables, and if we say effort or we use the letter E, we mean either force, voltage, torque, or pressure, depending on what system we're talking about. If you look on the right hand side, the velocity, the current, the angular velocity, and the volume flow rate are variables if depending on which system we're talking about with different units, guys. Yeah. The only thing you have is they are the same kind of variables, but they have different units. Okay, we are going to look at the relationship between those variables. There are four variables that we use. Two of them I already told you. Those are the efforts and the flows. But the effort is the derivative of the momentum variable, or you may say that momentum is the integral of the effort variable. And the same thing could be said on the right hand side, as you see in there, that the flow variable is the derivative of the position variable, which we're going to call it Q. So we're introducing two other variables besides the efforts and the flows. P is the momentum and Q is the position. So if you differentiate the position, you get the flow. Or the reverse could be said. If you have the flow, you integrate once, you get the position, which is important for our analysis, because in many situations we want to know where things are. On the left hand side, you can say that if you differentiate the effort, the momentum, you get the effort. If you integrate the effort, you get the momentum. So this little tetrahedron that you see in there is known as Painter's tetrahedron of state. This tetrahedron of state, just to remind us of the basic concepts, is named after Professor Henry Painter, who is the inventor of this technology. He was a professor at MIT, and in 1959 he had this vision that we could actually model systems in many energy domains if we follow the simple rules. And if we recognize that on different energy domains, while the variables are different and they have different units, but they belong to the same family of variables. So what Painter is saying is if you approach it that way, then it's possible to do modeling and simulation of a system that actually has variables in different energy domains, but is composed of components that might be hydraulic, electrical, or electrohydraulic, a combination of these, and that's what gives birth, you may say, to the term mechatronics, because mechatronics involves mechanical and electrical plus hydraulic systems plus rotational systems or thermal systems, Painter's tetrahedron state gives us a nice way of looking at that set of variables. This is a set of units that each one of those four variables would take on each one of the energy domains. But you can see why we're doing this. We're doing this because it's easier to do four variables than learn 16, right? So we'll take a very simple example to illustrate those variables in different energy domains. And if we have the simple system like the starter of your car, actually there's the battery, which would be the source, the starting motor, and then the Bendix. And now with different words, just words, and using those variables, we can put together a system that we are going to call it bond graph. See the battery, this is the bond between the motor and the battery and between the motor and the Bendix. These two communicate with voltage and current, and these two communicate with torque and angular velocity. All right, that's the basic concept, so we'll continue later.